We're talking about two variable inequalities, which means we're probably going to have an x and a y. We usually don't stray too far from the x and the y pattern. So with two variable inequalities, we have to think, well, is that going to be a line? Well, yeah, the stuff that we graph with x and y is usually a line, but yesterday we found out with an x and a y, if you use absolute value, you also have some decent graphs as well. So a two variable inequality whose graph is a region of the coordinate plane bounded by a line, doesn't want to slide, there it goes. Linear inequality, graphs as a line. These you've done before. And these you did in linear algebra, which would have been quite a while ago for all of you. So what you see here is what's called a shaded half plane. Because with inequalities, you don't get just one answer. You get an infinite amount of answers. X is greater than or equal to 3. Okay, well, I could put 4, but I could put 3.8, 3.9. Maybe I put 3.85. You know, and you just think, hey, there's an endless amount of them that I could actually have for solutions. So we solve these graphically because we want people to see, hey, it's all these things that we have. But we notice there's a difference here, kind of like that last problem with the similarities and the differences. And we say, wait a minute, this one's dashed and this one's solid. What's up with that? Well, if it's on the solid line, these are actual solutions to the graph. They work. That's what the solid means. But over here with the dashed, that's just a boundary line. It's a line that says, hey, these don't work, but all of this good shaded stuff over here, yeah, those are a go. So they are called boundary lines, but one gets graphed as a solid because the answers on that solid line actually work in the inequality. And then we have those shaded half planes. So a plane described in geometry as a sheet of paper that never ends. It just keeps going in both directions. And when that happens, we have to show people, hey, this isn't just a couple of answers in here. We want to keep going forever. And that's the shading pieces, which, by the way, you probably want some colored pencils out again today because we're going to want to graph out a couple of things at one time. But we want to make sure we're going to separate those in our notes. So down here, solutions to the linear inequality are represented by the shading. So where the inequality works, we find the shading. And it says, are the points on the boundary line considered solutions? Yes and no. And the way we see that, the solid is, yep, all of those will count. Dashed, nope, those don't work. And the difference between the two is as basic as an equals y. That's the difference. We will see equals, so this will be either less than and equal to or greater than or equal to is what we'll see for those solid lines. And this will be just less than and greater than when we're dealing with that boundary line piece, which is the dashed line. So to graph linear inequalities, I'll tell you the biggest mistake is we go too fast. We know how to graph lines already. So we say, oh, I've got some points, or I have the slope and the intercept, and we draw on that solid line before we even think about it. So this is the part where you have to kind of pause for a second and say, okay, I do know what I'm doing, but I have to be a little more careful. So what we're going to do is graph the boundary line. Doesn't matter if we use y equals mx plus b, or if we use the x and y intercepts. So that tells us it can come in slope-intercept form, it can come in standard form. We're just going to do what we do with lines when that happens. So slope-intercept form, find your b, find your slope, graph it, but do that little pause beforehand. Is this supposed to be solid or is this supposed to be dashed? Standard form, find your zeros. 0y, x 0, and then pause for a second. Dashed or solid. So we'll use a dashed line for less than, greater than, and we'll use a solid line for less than or equal to or greater than or equal to. So away we go. We want to test a point so we can figure out where to shade. We're going to find out there's another kind of shortcut. We need to think your way through that too. But really the safe way, especially if you're taking a test, is always just go ahead and test a point. Test a point to see which side to shade. Don't ever pick a point that's already on the boundary line. If you put that point in, it's going to make, well, if it has an equals bar, it'll make it absolutely true. We want to pick one that's going to be easy to use, but is not on that boundary line. If you get a chance, pick 0, 0. I mean, those are such easy numbers to work with. Plug it into the inequality. If it makes it true, that's where you're shading. You're shading on the side where 0, 0 is. If it doesn't make it true, well, then you're supposed to be shading on the other side. Now, I'm pretty conservative about this, especially when I'm taking a test. I will actually test 2 points. I'll test one on one side of the line and see if it works, and I'll test one on the other side. And that's because, we're human and stuff happens. We make mistakes. But you could get away if you're very careful with just testing 1 point. If it works, shade on that side. If it doesn't work, shade on the opposite side, and you'll be set. So linear inequalities, like I said, you guys graphed these, but it was just a long time ago for you. So this one says, what is the graph of each inequality? And what we really do is we pretend, quite frankly. We pretend it says equals. And we think, okay, so my slope is 3, and my b value is -1. So to graph this, I should go down 1, because my y-intercept is the point 0, -1. And I have this slope of 3. So I'm going to have to go up 3 and over 1. I have to think of that as a fraction. Up 3 and over 1, maybe do that a couple of times so you have something to aim at. But now comes the pause for a second. We were just pretending. We were pretending that it said equals. So now we look back up at the original and we see there is no equals bar there. So what we have on that line should not be included as part of the solution. We're going to have to make that dashed. That got a little crooked down there. I better put my slope to use here. And now, like they said, let's test a point, see if it works. And because 0, 0 in this one it's a little too close for comfort. It looks like it's not going to pass through 0, 0, but I might pick something a little farther out here that's still pretty easy to work with, a little number like 3, 0 there, and try it out. So I'm going to test 3, 0, see if it works. That would be a 0 in for y, 3 times 3 minus 1. Well, that's 9 minus 1, and that's 8. Is 0 greater than 8? No. So I'm not going to shade on this side. I'm going to shade over here instead. So we test a point. We see, wait a minute, doesn't work. You have to shade on the other side. Just be really careful with that 1 point. Like I said, if it's a test, I'm really conservative, and I'm going to check it in 2 different spots. Down here, looks pretty similar. We do our pretending. Slope is the same. B value, -1. Start at 0, -1. Up 3 and over 1. Pause. What's different about this one? It's going to be solid. It does have an equals bar, so this needs to be solid. Oh gosh, that's not even close to being aligned. That's a little better. Maybe just because I did a positive before, maybe this time I'll try and I can see pretty clearly that 0, 0 is not on that line. So let's try it. Is 0 less than or equal to 3 times 0 minus 1? So is 0 less than or equal to thank you. 0 less than or equal to -1. Oh, doesn't work. Well, now this time we shade over here. Wait a minute. Maybe there's a shortcut in here that we can see. Y is greater than 3x minus 1. And we shaded above the line. Y is less than or equal to 3x minus 1. And we shaded below the line. It works whenever you have your equation in slope-intercept form. If it's in that y equals mx plus b format, all you have to do is look at the sign to know which way to shade. Greater than, you'll shade above. Less than, you'll shade below. But only if you have y equals mx plus b. That's why I'm not even writing that down. Because testing a point is not a difficult thing to do. I'm not even going to write that down. But there's 2 of them here for you. So why don't you go ahead and graph those if you haven't already, which I know some of you are already doing it. I was watching you up here. Graph those 2. And check in with an elbow partner. Check in with an elbow partner. Check in with somebody. I want you to pretend you're grading their paper. You're going to check for dashed versus solid and shading on the correct side. Basically shading the correct Make sure yours are right, because what I'm going to do is call on some people. So get to know the new chicken wing elbow partners you got since the last seating chart. Ask them to take a look at yours, and you take a look at theirs. And some people are just finishing up, but find somebody around you now that looks like most people are done. Take a peek at each other's graphs. Make sure things are going right. Nick, what'd you do for this one? You do dashed or solid for this one?
Solid.
Solid? And then did you shade above the line or below the line? Everybody agree? Okay. Then this one, I guess I'll change colors at this point. Brock, what'd you do for this one? Dashed or solid? Did you shade above or below? Below? How many people use the shortcut? Since these were in y equals mx plus b, you didn't testify you want to use the shortcut. Yeah, and when it's y equals mx plus b, that's always safe. We just have to remember, if it's in standard form, you want to test a point. And some of you might say, well, if it's in standard form, couldn't I solve it for y equals mx plus b? You could. But every step that you take, remember you might make a mistake, you know. So with standard form, easier to go ahead and get those graphed by the zeros. When inequality is solved for y, how do we tell which half plane to shade? Well, if it's greater than or equal to, shade above the line. If it's less than or equal to, you shade below the line. And here's why it makes sense. You've got y by itself. So you're saying your y value needs to be greater than something. That means it needs to be higher. And if you have y by itself and it says less than, well then your y's need to be lower. So that's the reason that it works. But again, it has to be in slope-intercept form. Problem 2 says, going to go to the fair on the rides. You don't want to spend more than $15. Tickets are 25 cents. Small rides are going to need 3 tickets. And large rides are going to need 5 tickets. And how many smaller large rides can you ride? Okay, let's think backwards about this one. I don't want to spend more than $15. There's my total. So, could I spend exactly $15? Could I spend $14? Sure I could. Less than or equal to. But what I'm going to do is go on 2 types of different rides because I need small rides and large rides. But by putting 15 as my total, what I've just done is said this has to be about money. So I'll use X to represent my small rides and Y to represent my large rides. And I'm not just going to put 3 in front of X because that's not what the tickets cost. If I go on a small ride, how much does it cost me? 75 cents. That's how much it costs me. Remember, my total was about cost. How much does it cost me to go on a large ride? I didn't give myself enough room here so people in the back can see this. Doesn't look like so. So now we see where this whole standard form thing comes in. And yeah, you might want a calculator for this one. Totally up to you. We are talking about dollars, so maybe people will be just fine without it. But the easiest way to graph these is to do your zeros. Use your thumb method. Take it through. If this is gone, we need to know how many $1.25s will go into 15. Again, you might grab a calculator for that one. Oops, I want that multiplication. That'll give us 12 tickets. If y is 0, we cover up the y. We need to know how many 75 cents are in 15. And that's going to be 20. So we look at our graph, and we think, thank goodness, that's that nice 20 by 20 graph, and it's all in quadrant 1. Why quadrant 1? That's real life. There's not going to be any negatives. So we could just use 1 by 1s on this one. Again, I'm not going to label with 1s. 6, 8, 10, 12. Why does that look like right there? All right. We have 2 points to start, 0, 12, and 20, 0. Dashed or solid with this one? Solid. I'm actually going to cheat and use my straight line drawing here. Now these, it doesn't take so much thinking or even testing a point because it's a word problem. And you think for a second, if I only have 15 bucks, am I going to be able to do all of these rides out here? Of course not. That doesn't make any sense. I'm going to have to shade down here. Here's the second thing to think about. Can you go on 4.5 rides? This should actually be what we call a discrete graph. Discrete graphs are graphs that have countable number sets on them. So if we were really picky, we'd say, okay, you could do this amount, any of the nice grid points would be things that you could actually do. We're not going to be that picky. We're going to say, hey, everybody understands that, you have to use what's inside there, but you can't go on half a ride, But this is definitely where we start to pick up on the fact that there are some graphs that are what we call countable, and they're really discrete. So this isn't an infinite set because you can't go on a quarter of a ride, 3/5 of a ride. You can't do that. So this is a countable discrete graph. Even the book says, you know what, we're not going to have everybody put all those dots on there. Just be able, if somebody says, how many rides could you go on? You could say, well, I could go on 6 of the small and 4 of the large. I could do that. Be able to pick out some points, some answers that you could give to that. So down here, we got it says, suppose you decided and said you're going to spend no more than $30 for tickets. What are the possible combinations of small and large rides that you can ride? And then we already talked about the quadrant 1 fees. So here's what I would like to put out there for you. I'm not sure we need to do another one of these. So tell me how you're feeling about the word problem with the rides. 4, 3, 2, 1, 0 me on the word problem with the rides. Okay, then we won't do another one. Because it's just kind of silly. We've got this no more than 30. All we'd be doing is changing 30 to a 15. Or 15 to 30 in our last example. Now, sometimes we have to graph more than one, and that's why I said it would be good to have, the coloring type of things out so that you can see what's going on. Graphing 2 variable absolute value inequalities. Solve for y. Get y by itself. Notice it doesn't say linear inequalities anymore. Get y by itself. Graph, we're going to talk absolute value. So graph using the transformations that we know about, the a, h, and k that we know about. Now here was where we really have to stop ourselves. Here's why. Absolute value graphs are new to us. We were really good at them. We did them really fast because we're really good at them. There's that mistake that can happen again. If we don't pause and say, dashed versus solid, everybody's going to solid these up every single time because that's what you're used to already. And then shade the appropriate region. We certainly can use a test point for this as well. Just pick a point that's not on your V and test it out. Does it make the inequality true? Then that's where you shade. If it doesn't, shade the other way. That's how it works. So now in problem 3, that just looks weird. And you had some of these in your homework yesterday where you had to move things, you had to manipulate them. That's what we're going to do in Algebra 2. We're going to become master manipulators of numbers and letters. So, bless you. We look at this and say, okay, what I would have to do is I would have to move this 1 over. All right? So let's do that. There's still something wrong with it, isn't there? What else is wrong with it? Here comes the trouble. Because when we divide or multiply everything by a -1, what do we have to do? Yeah, don't forget to flip your sign. And if you're thinking, okay, where do all the negatives go? Remember, there's a little imaginary 1 out in front of that absolute value. It's 1 times that quantity, absolute value of x plus 2. So 1 divided by -1 would give us a -1 in front, and then -1 divided by -1 would give us a +1 back here. And from there, you know, we found out yesterday, it's not a tough thing to do. What we're going to do is we're going to say, all right, so my vertex, opposite of what I see in there with the x's, but the k value for my h and k is right back here. And we're going to start at -2, 1. Now, what did you do yesterday to finish that, to get the rest of the people? Yeah, slope. So we look at this and we say, well, the slope here is a -1. So -1 over 1, I'm going to have to go down 1 and over 1, which makes perfect sense because if it has a negative, we know it's supposed to open down. This guy was small. Then we could use our slope backwards. But we do have to pause. And we did really quickly yesterday. We have to pause. Because is this one supposed to be dashed or solid? Dash. That's going to catch us. You know, it just is. And then, because this is the first time we've seen this, we don't know if that same shortcut that we used before is going to work for this. But let's give it a try. I mean, if the shortcut works, we should get something above this that would work. So, I'm going to try something obviously above it, like 0.4, and see if it works. So let's see. That would make this a 4. Just testing a point. Let's see what we get. 0 plus 2 is 2. Absolute value of that is 2. But we have to strap a negative on it. And that'll give us -2 plus 1, which is -1. Is 4, in fact, greater than -1? It is. This works. So we shade everything above. So far, so good. It looks like the greater than thing is still going to be above. So, let's put on this one. Y minus 4 is greater than or equal to 2 times the quantity x minus 1. Is that ready to go? What's wrong with it? Okay, can we move it over? Sure. Where's the new vertex for that? 1, 4. What should we use as a slope? 2 over 1. Slow down. Dash your side. Now we kind of see why it's important to test the point. Because if you look at that and you say greater than, oh, wait a minute. So is that going to be the stuff in here, or is that going to be the stuff out here? And the easiest point to test, especially for this one, would be 0, 0. So if greater than is inside it, this should not work. So let's see what we get. 0 is greater than or equal to 2 times the absolute value of 0 minus 1 plus 4. 0 minus 1 is negative 1, but the absolute value of that is 1. Is 0 greater than or equal to 6? No. So if this doesn't work, then the only other thing that could work is the stuff that's inside. And that's what we have to shake. So when we think about the shortcut, yeah, you look at this and say, okay, this is the problem. Is it in here or is it out here when you do greater than? So the shortcut is fantastic, but reasoning-wise, you might just want to test a point. So now, this is supposed to be difficult. What inequality does this graph represent? Well, let's get the V shape first. Where's our new vertex? 3, negative 2. Can you count this one? Is this one kind of obvious? What is it? So we notice they're going by ones, even though this is labeled with twos. And you're either going up 1 and over 1 or up 2 and over 2. Maybe 1. So there's our V shape. We have to figure out what goes in here. What does your instinct tell you from the last one we just did? Greater than? Okay. Greater than, should we use equals? Dashed. Now, if you're worried, well, is it really greater than? Now test a point. Check and see. 3, 0 better work in your new inequality, or you picked the wrong way. There's always a way to check these. So, done? Have everything we need? There it is. Try this one. See what you get. We want to warn everybody this one does go by twos. The other one went by ones. This one's going by twos. So far, it looks like that's not an issue for everybody. I mean, looked at it and saw that, but it does look like a few people are saying, ooh, what's going on with the slope here? Remember, if you're ever worried about that, you can pick a couple of nice grid points, and then you could use the slope formula. So you could say, I've got -2, looks like -2, 3 right here. Another halfway decent grid point might be 0, -1/2. So if the counting isn't working for you, you could always use y2 minus y sub 1 over x2 minus x sub 1. But what was the slope on this for those of you that found it? Come on, I have lots of papers that had on there. What was the slope on the right side of the graph? Who wants to take a chance? I'm going to pick somebody to tell me. Jack Millis, way in the back. What'd you put? Yeah, it's the slope of a -1. So, you know, we'd say, well, we don't necessarily need the 1 there. And then last but not least, we need to make sure we get the right inequality in there. What is the right inequality for this one? Everything's above, greater than. Again, if you're worried about that, put greater than, test a point that's already up here that you know is supposed to work. If it works, you know you're right. If it doesn't, then you say, well, I must have switched it around. It must be less than. So now this last one says, we know that when things are solved for y, we can just go ahead and if it's greater than, shade up, and if it's less than, shade down. So you can tell from looking at this inequality that you need to shade above y greater than. That represents your solution. Could we use that same method with this one? We shouldn't, because this is in standard form. But could you solve this for y? What's going to be the one glitch on this one solving for y? What is it?
Negative.
Yeah, it makes sense. We're going to have to divide by a negative, so we're going to have to flip the sign. So that's the one glitch. All right, that was the 4 example thing that we had to get through today. So, 4, 3, 2, 1, 0 me first. How are you feeling? It shouldn't be too bad. Yep, that's what I'm expecting. So a little practice, and you're going to feel a lot better about these. Because really, the only piece we were missing on this was, should it be dashed, or should it be solid, and then which way to shade. But I will warn you, this test happens all the time. You know, the rest of the stuff in this chapter was not the most challenging stuff for you. So people get rocking away and they get to the last problems on the test, which involve this, and it happens all the time. People make a solid line instead of a dash. It happens. So slow down a little bit. Make sure things are going right for you.
Really don't, should I be out there? Really don't